Hi class, welcome back. Today we're going to discuss 4.2, the area. So let me just correct this real quick. This is supposed to be a 2. And there you go, easy fix. There you go. Alright, so what we're going to do in this section, we're going to introduce a process that will allow us to find the area under the curve. Now, this process is very sophisticated and actually pretty cool if you guys think about this. And I'll elaborate more as we go on. But if you guys think about this, we only have able to find the area of of famous or known geometric figures. But this is actually going to allow us to actually find the area under a curve, right? It doesn't matter what the shape of this curve is, as long as we know the function of it, we're going to be able to find that area. So we're not stuck to or limited to just a geometric figure. So, and the concept, well, anyways, I'll talk about that more in a second, but the objectives are to learn review some sigma notation and to be able to write them and evaluate them. Understand the concepts of area, approximate the area of a plane region, and then find the area of a plane region using some limits. So we will talk about limits today again, and we'll talk about some series notation. All right, so sigma notation. So you guys are part of the purpose of this course is that you guys learn about series. So I'll talk about this briefly, but I hope that this is sort of a review. So a sum or a series is the process of adding some terms, right? Now you're able to describe these terms by this formula known as a sequence, and in this case you're adding all these terms starting from the index 1 all the way until you go up by integers, by whole numbers, all the way to the end, right? So if this is 5, then you start with 1, you plug in 1, plug in, and then you plug in 2, and then you plug in 3, plug in 4, plug in 5, and then plug in, and then that's where you're done, right? So I is known as the index of the summation. A sub I is the ith term, right? Because they're all terms. This is the ith term of the sum, and the upper and lower bounds of the summation are n and 1. So this is the upper bound of the summation and the lower bound of the summation. So here are some examples. If the sequence that I'm trying to describe here is defined as I, and our upper bound is 6 and lower bound for the summation is 1, what we're going to start with 1, plug in 1, so that's your first term. Plug in 2, that's your second term. Plug in 3, that's your third term. Plug in 4, plug in 5, plug in 6. That's where you end, right? When you plug in, when your ith index is the 6th value. And that's it, right? And you can add these numbers. Right now we're just trying to expand this. So what about when you have the index starts at 0? And that's fine, right? You can start at different values, as you guys will know. I equals 1, I equals 0, I equals, j equals 3, k equals 1, I equals 1. So we can use different indexes, and don't get too caught up too much with the index and the variables. They're just dummy variables, right? So plug in the 0 first. 0 plus 1 is 1, so that gives you the first term. Then plug in, the next one will be plug in 1. So 1 plus 1 is 2. The next one is plug in 2. 2 plus 1 is 3. Then plug in 4. 4 plus 1 is 5, right? So and so on until you plug in the last one, 5, right? Plug in 5. 5 plus 1 is 6. So there you go. So you got all the summation. Let's try a few more. Plug in, start with it says here that j starts at 3, so replace j with 3. So first one is 3 square, that's your first term. Then plug in 4. 4 square gives you a second term. Plug in 5. 5 square gives you the third term. Plug in 6. 6 square gives you the fourth term. And then plug in 7, and that gives you the last term and also the fifth term. Now in this example, we can see here that we're getting different more variables, and we're making this a little more complex, but 1 over n is not the index, right? In fact, that's just if in this case we can consider this as this does not depend on the summation. We can actually even factor this out if we want to. Anyways, we'll see that sometime later on. So here, the only thing that is changing in every single term is the k, right? This tells you what is changing. So k1, that gives you 1 squared plus 1, gives you 2, right? Or that gives you that times 1 over n. K equals 2, gives you 2 squared plus 1 times 1n. K equals 3, you have 3 squared plus 1 times 1n. And then, because we don't know what n is, it's often for us to just put an ellipsis between them. We're going to say continue with the pattern until you plug in the last term, which will be k equals n. So n squared plus 1 times 1 over n. Similarly over here, which is what we're going to see more often in our class, it will be you have a function n times delta x, and then here your index is I. And so what's happening here is that this is changing, right? So first I equals 1, so that'll be f of x1 times delta x. Then plug in 2, f of x sub 2 times delta x. Then I equals 3, and that will give you f of x sub 3 times delta x. And the last one will be n, so that when I equals n, that will be f of x sub n times delta x. And so we put the ellipsis again to tell the reader that we're following the same pattern all the way over there. So that we can all see that the pattern will continue, right? We got to write at least 2 of them to see the pattern. All right, so there is a few cool properties that we can follow from here, and that I mentioned already. If k does not depend on this index, then we can treat that as a constant. In fact, it's a constant, and we can actually factor it out. This actually also works in the case where you actually have this, right? Because n does not depend on I, right? This is the one that is changing. We can actually factor the n out, and we get this, right? So it's also common for us to do it. Again, what I'm trying to focus, when I want you guys to focus, is that the only thing that needs to stay here is whatever is affected by the I. In this case, not the n, right? All right, so also if you have a summation where you have index of 1 or whatever index it is, and you end on upper bound is n, then obviously these are subscripts of the index I. What we're saying is that you can separate the two summations. And actually this also works backwards, right? If you have 2 of them where they're starting the same bound and finishing on the same bound, and they're both indexes of I, then you can actually put them in the same series. So it works both ways. But what we're trying to get here is actually we're going to be using this a lot right here, these 4 formulas. No need to memorize them. We'll give these formulas in the test. So this will be given, I'll put a note here, will be given for the test. Right. So for those who are listening to these lectures and following the lectures, good job, and you guys will now know that this will be part of the test. But they're not hard to remember, and I encourage you guys to try to remember these. So I actually memorize them, and they're kind of fun to memorize them. But anyways, what we're saying here is some of these were so interesting, but what we're saying here is what we're saying is that you can the sum of all these terms from 1 all the way to n, it's equivalent to Cn. The sum of all terms, you have 1 plus 2 plus 3 plus 4 is the same thing as n times n plus 1 over 2. Like over here. So if you guys notice, this example has it's starting at 1, right? And instead of adding all those terms, what you can do is use the 6 notation up here, and we suggest that we have is going to be following the formula that we have here. I'm just following this formula right here. what I'm saying here is I'm able to follow that formula wherever my 6 is going to be my n. So it'll be 6 times 6 plus 1 over 2. And this will give me 6 times 7 over 2, which will be 3 times 7, which will be 21. So if you add these numbers, it's the same thing as 21. So if you guys think about it, it's kind of like you're adding without adding. Does that make sense? Like you have these special formulas that allow you to add without actually being to add, just by following this formula. And we're going to be using them a lot. So please know them and be familiar with them. So you have the I square, and the I cube, and then I'll have you these 3 formulas. So we're going to use that in the next example to help us sort of add a few terms without actually adding. So here we go. So this is the problem. It says evaluate the sum. And the sum, it looks like this, right? This is your upper bound, this is lower bound. Sometimes I have to write them like this because the software that I use for math is not as friendly, but they're the same thing, right? This is the upper bound, this is the lower bound. And then we're going to add all the way from 1 to 10, from 1 to 100, to 1 to 1,000, 1 to 10,000, right? Imagine if you actually had to add all those numbers. It will be exhausting. And so I think if you guys think about it, like a lot of the formulas that were generated back in the time, they were motivated because they didn't have calculators, right? So they were actually always trying to find a way to make calculation more simple. So it kind of makes sense. All right, so let's try let's simplify this. We're gonna use the formulas above. So if you guys notice, we're starting with this, right? And what I'm gonna do here is I notice that n squared does not depend on I, so I'm gonna factor that out. So there you go, 1 over n squared. Now, why did I put a 1 on top? Can you guys think about it? Why? Well, this is a denominator, so it has to stay under something. So, well, I cannot just put a 2 there because that would change the value, so it has to be under a 1. Then you're left with I plus 1. It's important for us that we keep the parentheses, and we know that we had parentheses because we had a fraction bar, and that's grouping them together. So we'll keep the parentheses here. This is multiplication right there. And then now we're going to separate these to their own summation. So we're going to have the summation for this one and the summation for that one. So we end up getting this. Now, if you guys notice, this has one of those formulas above, and actually is going to be n times n plus 1 over 2. I'm going to put a bracket because this whole thing needs to be multiplied to the entire sum, right? Do you guys see that? This is multiplied to this whole thing. Well, this whole thing is this whole thing. So it's important for us to put parentheses. I hope that kind of makes sense. If that was your instinct, trust your instinct. So we're going to have 1 over n squared times whatever that is. The first one is, according to the formulas above, is n times n plus 1 over 2, plus, and this one is 1 times that, right? When you have a constant, it's just going to be the constant times the n. So that's just going to be that. Now remember that these formulas are special, right? And these formulas, you got to be familiar with them, but they only can start with 1. They have to start with 1. They have to start with 1 and end with n in order for us to use these formulas. All right, continue with this. What I'm going to do here is I'm going to distribute the n squared to both of them. So we have n n times n plus 1 over 2n squared, right? By multiplying these to here and that one to that. And so what we end up getting is these two expressions. Now, we could have common denominator, so to make sure that we can simplify them. And we're going to multiply this by 2. Well, actually, we're going to notice here that we're going to simplify these by canceling that one with that and this one with that one, right? So we're left with 1 over n and here, and we have n plus 1 over 2n. So we're going to multiply this by 2, so that we can have, that's a product, 2 times 1. And then we can have the same denominator, so therefore we can just go ahead and add them together. N plus 1 plus 2 will give us this over 2n. This will simplify to be n plus 3 over 2n. And there you go, right? We found what this equals to. And then now it's as simple as just replacing n with 10, right? So replace n with 10 into this formula, and that will give us that. Replace 100 with n with 100 and into the formula, and that will give us this. Replace n with 1000, and that will give us this. Replace n with 10,000, that will give us this. Do you guys see how much efficient this was? It was way easier, right? All right, anyways, I hope you kind of value that, and we're going to use that again and again, right? So it's actually going to be an important factor of our process of finding the area. All right, so let me talk about a little bit the history of the area, right? So it is known that we have a lot of geometric figures, and we have developed formulas for finding the area of these figures, right? And a lot of them they just came from either the rectangle or so on and so on, right? So we're able to adjust them, and so we're able to find the area of this one, that one by subdividing into triangles, and then be able to sort of calculate the area. One of the problems that we actually had, the mathematicians had, was finding the area of the circle, because that was not like it didn't have the corners, it was not able to relate it to the square or the rectangle or so on. But there is actually a way, right? And so Archimedes actually had was one of the greatest I want to say physics engineers, but he used a lot of math, right? And he had a lot of ideas. One of his ideas that he had was very interesting is that he was able to calculate the area of a circle by creating triangles. Now, one of his arguments was that he could make this very accurate by making the triangles even smaller. The smaller they were, if you guys notice, compare these, right? He was able to find the area of the bigger triangle, and then subtract, and they were able to subtract sort of, or find the average between this area and this area, right? So that gave us that area. But there was some error. But he realized that if you make more triangles, then the error is minimized. Do you guys see that? The error gets minimized if you make more triangles. Well, this concept is known as known as exhaustion. I don't know if maybe the name came from the idea that you're pretty exhausted because you're adding 12 triangles versus 6 triangles. So there's a benefit and a disadvantage, right? You're doing more work because now you get to add more triangles. But in the process, he was able to actually compute this and manipulate it so that you don't actually are adding 12 triangles, but you're actually manipulating the algebra and be able to simplify it, the process with some algebra techniques. But I mean, it wasn't as sophisticated as now, but that was the concept. Here's a nice video for you guys to kind of see if you guys want to, that talks about the exhaustion process. So let's talk about this concept. Let's continue with this, because this is going to help us understand why we're doing the following things. So let's find the area of a plane, on the region, right? So we promise that in this section we're going to learn how to find the area under the curve. So in this example, you have a curve. This is your curve. F of x equals negative x squared plus 5. And our goal is to only find the area between x equals 0, which is right here, x equals 0, all the way to x equals 2. So we're bounded to just find the area between those two, right? For now, let's limit ourselves to this so that we can come up with some nice result, and then we'll generalize it later. So are you guys okay with that? We're finding the area under the curve. Now, the way we're going to do this, instead of using triangles, we're actually going to use rectangles. In fact, if you think about it, a lot of the formulas from the geometry came from rectangles. But anyways, so what we're going to do here is do you guys agree with me that if we subdivide this region into a bunch of rectangles where the width is always the same, right? Let's just call this width to be 2/5. So 2/5 plus 2/5 gives you 4/5, plus 2/5 gives you 6/5, plus 2/5 gives you 8/5, plus 2/5 gives you 10/5, right? We're sort of subdividing this, right? Now we can come up with the height of this because we know that x equals 2/5 here, right? So this point right here, the height of this, is equivalent to the value of the function at 2/5. So you're able to find the height, right? This right here is the height because that's f of 2/5. So if you know the width, right? If you know the width and you know the height, aren't we able to actually find the area of the rectangle? And we do, right? And what we're gonna do here is we're gonna just do that, right? We're gonna actually multiply the width times the height, and this will give us this area, and do the same thing. Width times the height, we get this area. Width times the height will give us this area. Width times the height will give us this area. Width times the height will give us this area. Now if you guys notice, there will be some error, right? There will be some error right here, error right there, error right there, error and error, right? So, but nonetheless, we actually have a good approximation of what the area under the curve is. And that's the idea, right? That's the idea. That's what we're going to be doing, and we're going to develop a process. We're going to have to discuss how can we define this width, how can we define this height, and can we approximate this even better, right? And what other approaches can we use? So that's the whole concept. So if you guys notice, we're just adding a bunch of rectangles at the end of the day. So do you guys see where the summation will come in, right? So the way we're going to do this is, let's generalize the process. So let me erase some of these stuff right here. So we mentioned that all we're doing is just adding a bunch of areas of the rectangle. Sorry, I was trying to erase that. And so if you guys think about it, let's think about this for a second. So if what we're going to be doing is we're going to add, if you guys think about this, is 2/5. This actually is, if you guys think about it, this is 2/5 times 2. Isn't that's the same thing? 2/5 times 1. This is 2/5 times 2. This is 2/5 times 3. This is 2/5 times 4. This is 2/5 times 5. So if you guys notice, the only thing that's being changed is this. So this actually tells us, this suggests that we can actually come up with these values by using this formula, right? We can say that 2/5i will give us those values, right? And we notice that those are very important because those are the points that we're going to be using to plug into the function so that we can actually get the height. So do you guys see where we're getting that? The height. I'll show you guys how we find those much quicker without looking at the table, by looking at the graph. But I'm just trying to tell you where the whole thing. So the height will be f of this number, right? These numbers. So the way we're going to describe them is by putting a value. The input will be depending on the index. And then if you guys notice, we're going to come back here and we're going to multiply by the width. Since our width is going to be the same, right? It's always going to be 2/5. Then we can always just multiply the height times the width, and that will give us one rectangle. And then we try this again with I equals 2, and then I equals 3, and I equals 4, and it keeps adding all the terms, right? So it seems like we're going to be adding a bunch of rectangles, right? It seems like we're just going to be adding a lot, right? But remember that we don't need to add a lot, because what we're going to be doing is we're going to be using those series, the notation that we learned for the summations. So that's where that's going to come in. It's going to help us add these much quicker. So here we go. Let's try let's find this right here, and let's find this right here. So let's begin by finding the width. That should be your first thing. In the problem, usually it's going to tell you to use how many rectangles you're going to be using, right? The problem is going to tell you use 5 rectangles, use 10 rectangles, or use 7 rectangles, right? and it's also going to tell you from where to where, right? So the way we're going to do this is you're going to take the whole width of this boundary, right, from x equals 0 to x equals 2, and what we're going to do is you're going to subtract that distance, so 2 minus 0, and then you're going to divide it by how many rectangles you need, right? Because you're going to divide this by 5 equal parts, right? 5 equal parts. So that's going to be 5. So you guys see, that kind of makes sense, no? That's almost like it feels kind of natural, right? So you have the whole distance and you need equal width, so you divide it by 5. So that gives you 2 over 5, right? Now so that gives us the width, so that's going to be our delta x. That's going to be known as our delta x. And you guys will see that notation coming up over and over again. So it'll be pretty much our delta x will be defined, as you guys will see, it'll be b minus a over n, and n depends on the number of rectangles we're going to be using, and the last one here will be your b, and your initial value will be a. Now there's a problem with this because well, not with this one, but the problem with finding the value, this value right here, the input of f, we need to be careful, because we could start at 0, we could start at 2, or we could start at 1 or 1.5. So what we need to do is some adjustment, right? So we're going to call that xi. So that xi will actually depend on where we start, and also is going to depend whether we're doing a reference to a left point or a right point. That's also going to matter. So we're going to go more in detail of that. For now, I want you guys to also make a point here. I want you guys to focus on this part right there. This is f of this. So this is your input to f. So you have to actually rely on the actual function of f. The actual function of f, which was given up here, x minus x squared plus 5, and plug in 2i over 5. And all you're doing is replacing x with 2i over 5. So you have a minus in front of it, you have a square there, and you have the plus 5 there. So that's the part of evaluating at f. All right, so I'm going to erase this just because I want to keep it clean for you guys to make your own notes. All right. All right, so let's find this. Let's get a little more sophisticated with this, right? And in part B, instead of using the left side, instead of using the right side, we're gonna actually use the left side. So instead of using as a point of reference the height, the right side, we're actually gonna use this one. So the way we're gonna be able to get this will actually give us this point as the height. So the height will be bigger. Do you guys see that? If we make a point here, the height will be bigger if we use this as a reference, right? If this is our initial value. For part A, we use this as initial as our first one. For part B, we're using this one, so it makes a difference between both results, and it's actually common for us to use either one. So one is referred to the right side, one is referred to the left side. So let's see what happens there. So for this one, if you guys notice, delta x does not change. Delta x is still the same. Delta x is still the same. It's going to be 2 minus 0 over 5. This will be 2 over 5. Right, so that's still the same. The only thing that's going to change here is the xi, right? The input into the function. And the way we decide whether we're going to use the left side or the right side is the one by saying, well, which one is going to be much simple for us to try. If you guys notice, this one looks a little more complex. And we'll talk about where are we getting these values, right? We'll talk about how I can show you guys how to get these values. For now, the purpose of this is to overlook and to generalize the process. I want you guys to think about that in part B, we overestimated. In part A, we underestimated the same graph, right? The same area. So we can say that the true area of the region will be between the two values, right? Between the underestimating and the overestimating, right? All right, so we're gonna get better, right? But I'm just trying to give you guys some some context here. All right, so here we go. So we're gonna start to develop our technique. We need to set up the series, right? We need to find the series. This is what we need to set up. So we have a lower sum, or we're gonna have an upper sum, and we can see the upper sum and the lower sum, how they differ, because one is gonna give us an overestimate and the other one's gonna be a underestimated. Either way, if you guys notice, you always have to know your delta x. So these are the two components that we need to know: delta x and what is f of mi. Now, this will depend whether it's going to give you a lower bound or an upper bound. So let's begin by using the delta x. As we said before, if you're looking to subdivide the rectangle into n rectangles, then what we're going to do is we're going to use the endpoints, which they're always given, and subtract those two, and then divide it by n. So that should be the easiest one to find. Then, depending on the expression, we can find out the left point, if you're using the left point versus the right point, by using these two formulas, and I'll explain them in a second. So with the right point, it's so you're always going to start. This will depend on your starting point. So in this case, this is always a. In fact, I can start writing a general formula for this. So your mi is going to be your starting point plus I minus 1 times delta x. Your mi is going to be your starting point, which is a, plus I times your delta x. So do you guys notice that this tends to be much simpler for us to work with than sometimes working with this? But it just depends on what they're asking us to do. All right, so let's use, this is how we're going to figure out our m's, right? Our midpoint, sorry, not midpoint, but our value of x. So let's go ahead and do this, right? We're going to do it both ways. You guys will see me doing it in this two different ways. So let's try the left point. The left endpoint will require us to use this application right here. So we're going to have, using the formula above, a equals 0, because let's look at the problems here. It says find the upper and lower sums for the region bounded by the graph. F of x is equal to x squared, and the x-axis between 0 and 2. So here is our graph. Here's 0, here's 2. We're finding the curve between the function and x-axis. We're going to use both the upper and the lower. So we'll start with the lower. The lower has to do with this case right here. So the lower will be, so using the formula a equals I minus 1 times delta x, our first thing is to find delta x. So delta x is going to be by looking at the endpoints, right? This is your endpoints. So take 2 minus 0. So this is your a, this is your a, and this is your b, right? They're always going to be your a and b. So we're going to take 2 minus 0 divided by n. In this case, we don't know how many intervals we're doing, but that's why we're going to leave it as n. So when we're not specified, we're going to be using n as the number of intervals. All right, so we're going to leave that as an interval as n. So we have 2 over n. So that's your delta x. And so when we use this one, sorry, I made a mistake here. That's going to be our little m. If you guys notice, in this example, a equals 0. So a equals 0, and I did another mistake here. This is a plus. I minus 1 times delta x, and delta x is 2 over n. So there you go, right? We don't have to think too hard for this, because this actually always gives us that number. So we have 2 over n times I minus 1 is 2 times I minus 1 over n. So we got everything we need. We know what this is, and we know what mi is. So now that we know those two things, right? Now that we know those two things, Now let's go ahead and simplify it. So so replace this with 2 over n, and then replace this for x, right, in the function. So where's your function? Function is x squared. So take this and plug it in into the function. So all you gotta do is, if you guys notice here, I did that step right there. So f, the series of plugging in your m, which is this, and then when you do that, when you plug into f, that means you do that by squaring your input, right? Squaring your input, which is this whole thing. All right, so I hope this kind of makes sense, right, up to here, because what we're going to be doing now is going to be purely algebra. So let's go ahead and find by plugging in and doing some algebra here, we're going to go ahead and now plug in the simplify it by squaring everything. So let's square everything here, and all right, so we're gonna square the 2, and we're gonna square the n. So that's how we get 2 squared is 4, and then n squared is n squared. And then we're also gonna square this one times 2n. Now we know that this does not depend on I, and this does not depend on I. So what I did, it was multiply them and then move them outside the series. Why? Because I want this to be as simple as possible, right? I want my inset to be as simple as possible. What I'm going to do now is I'm going to distribute the value. I'm going to distribute I'm going to expand this part of the expression, and that's how I got I squared minus 2i plus 1. And then with this from the series, right? And then from there, I ended up separating each of the terms into their own series, right? I left a big bracket here to tell the reader that I'm multiplying this to everyone. And then once you have that, then what we can do here is, if you guys notice, when I did it to this one, I left the negative 2 outside so I can have the I by itself. And then that way it's easier for me to recognize which formula I'm going to use. According to the formulas above from the summation, this I square, the summation of this I square is going to be n times n plus 1 times 2n plus 1 over 6, followed by minus 2 times the sum for this, which is going to be n times n plus 1 over 2, plus 1 times n, which is n. And then this just becomes a algebra problem. What we're gonna do here is we're gonna expand. We're gonna note here that there is an n that can be canceled for every single term, right? Remember that this needs to be distributed to everyone. So before I did that, I sort of distributed the over n, and that's how I was able to have n squared. And then just cancel those two. Why I did that first is because if I didn't do that, then I would have so much to work with here. Why? Because then I would have to do n times n plus 1 times 2n plus 1, n times n plus 1. But if I did that and simplify it, and I did it correctly, right? Because this needs to be distributed to all 3 terms. Then this made it easier for me to just expand it and then distribute this to both terms, and then this is just going to be 1, right? But in the same occasion, in this line, I ended up also I did another step. I actually not just expanded it, but also I have them to be the same denominator. So this will be by multiplying this by 3 and 3. Right, we'll have a common denominator, so I multiply by negative 6. That's how I got this one. And I multiply this by 6 over 6, and that's how we got 6 over 6. Then once I had that, I realized that if I expand the negative to both of them, the negative 6 and the 6 will cancel each other out, leaving me with this. This whole thing gets canceled, and then leaving me with just negative 6 over 6, and this, which I can combine them by combining it with the 3n, and that gives me negative 3n plus 1 plus the 2n squared, and then over 6. But then I simplify the 4 and the 3 because they had a common factor of 2, so that gives me 4 over 3 and square. And so what I end up doing is I distribute the 4 to everyone in there, so that gives me 8 n squared minus 12n plus 4 all over 3n squared, 3n squared, 3n squared, and then cancel those as much as I could, right? And then cancel those two, gives me 4 over n, and then this one cannot be canceled, so that left me with that. And that's it, right? For now, that was it. In a similar argument, I can do the same thing for the upper. In that case, if you guys notice, the formula suggests that we just have the initial value plus I times delta. A in this case is 0 again, plus I times delta x, which is going to be 2I over n. So this is going to become a little much easier because when I plug it into our formula, right, and we know where the formula is coming from. This is the rectangle. This is the product of the rectangle, right? The area of the rectangle, height times width, and you're adding all of them. So when I plug in 2I over n into the function, this will give me 2I over n squared times the delta x. Square the whole thing, that gives me 4I squared over n squared. Now again, I know the 4 and the n squared and the 2 and the n, because it's a product and they do not depend on I can factor it out. So I'm only left with this summation. And this summation of I, following sorry, that's an I square. That's an I square. Following the summation formulas above, this will give me n times n plus 1 times 2n plus 1 over 6 times the factor outside, which is a over n cubed. Then what I end up doing again, as I did before I start multiplying this whole thing, I don't want to multiply that. I mean, that's a lot of work. So if I can find something that I can simplify, it would be nice. So I simplified these, right? And this became a square. So that and then I simplified this to become a 4 and this to become a 3. So that made a little my life a little easier. This will be 4 over n squared. This will multiply. This will give us n plus 1 times 2n plus 1 over 3, and then we can expand this by having 2n squared plus 3n plus 1 over 3, and then expand the 4, which will give us 8n squared plus 12n plus 4, right? Because you're going to expand it to everyone. Why? Because it's a fraction bar and there's a form of grouping. And multiply this together. And then, now that we have this, then we can go ahead and then divide every term, right, by the denominator. And that gives us, these will cancel each other out. These will partially cancel. And then, so we're left with this expression. And so the upper sum will look like this. Right. So now this is just the upper sum. There's actually more context that we want here. So what we notice here is we're gonna now use the exhaustion process, because we left it to this idea that n represents the number of rectangles that we're doing. Well, if we have more rectangles, right, in this curve, if we have more rectangles, then we become more accurate because the error becomes smaller. So how big should we make this? Well, can we make this like 1,000 rectangles? Would that make it more accurate? Yes, it will make it more accurate. But what will make it more accurate? Well, what about 10 million? With 10 million rectangles? I mean, this is gonna be so small, right? So like you're barely gonna be able to see rectangles in there. But it's gonna become more accurate. Well, what about if we use the exhaustion process? Like, what about if we actually just go crazy and say, what about if we have infinite rectangles? What about if we have infinite rectangles? What would that have? What would that do? Well, that would make it just exactly the area under the curve. If you guys think about that, because the error will be none, right? And so that's what the limit of lower and upper sums is saying. In theorem 4.3 says, let f be a continuous function non-negative in the interval from a to b, then the limit as n goes to infinity of both the lower and upper sum exists and are equal to each other. And thus, the lower bound and the upper bound of the area, right, they become equal to each other. So therefore, the area of the curve is going to be equal to those two. So what we're saying here is, if I apply the limit as n goes to infinity here, this is actually going to give me the area under the curve, which, if you guys think about it, if you apply the limit as n goes to infinity, this becomes 0, this becomes 0, so you're left with 8/3. So the area under the curve will be 8/3. Let's try that out for the lower upper sum. This goes to 0 as n goes to infinity, this goes to 0 as n goes to infinity, so the answer will be 8/3. Again, we get the same answer. So by doing that, not only we just approximated, but actually we found the exact area under the curve. Isn't that kind of cool? I think that's fascinating. Imagine how sophisticated that is, right? Now we're able to find the area under the curve. And so we say on this region, let f be a continuous and non-negative on the interval of a to b. The area on the region bounded by the graph a and b and the x-axis can be found by saying the area equals the limit as n goes to infinity of this summation, where again, this is the rectangle, this is the width of the rectangle. We already know how to find the width of the rectangle, and we are know already how to find this value. Now this value, let me just say this, it doesn't have to be the end point of the rectangle or the any of the end points of the rectangles. Actually, it could be any point between the width of this rectangle, right? So it could be any point between here. It doesn't really matter. It's actually going to give as n goes to infinity, it won't matter. So we'll still get the same result. So there's many ways we can actually find this, because the way we choose to have our C of I. All right, so since we can do that, well, let's try that in the next example. So finding the area by the limit definition. Find the area of the region bounded by the graph f of x equals cube, and the x-axis. So we're finding the area under this graph and the x-axis, and the vertical lines x equals 0 and x equals 1. So we need to bound it from the top, bound it from the bottom, bound it from the left, and bound it from the right. We want to make sure we represent this region, all right, as shown in the left side. So we already know how to find delta x. In this case, is going to be 1 minus 0, right? Let me do that again, right? Delta x is equal to b minus a over n. So we're going to have 1 minus 0 over n, which is 1 over n, right? So we found delta x. Now the goal is to find the area on the curve. Now we have a choice to use mi equals a plus I minus 1 delta x, or a plus I times delta x. Did you guys found that this was much convenient to use, because that was actually made everything much easier? Well, why don't we just continue with that, right? So if we use this instead of the left side, and it doesn't really matter which one you use, right? Because either one will give us the same result, will give us the same area. So let's use the one that is easier to work with, which is this. So using this, a is 0, right? A is 0. And so this is 0 plus I is just going to be the index I, and then delta x is 1 over n. So this gives us the number in between, which will be equal to I over n, right? I over n. So let me give you guys that extra note there. This is 0 plus I times 1 over n. This is 0 plus I over n is just I over n. So that gives us the upper bound input value. So it doesn't really matter, we call it mi or ci. In general, we're just going to call it ci. And so we're going to apply the limit of this series. Notice that I added this limit here from what we already worked on. So again, rectangle with summation from 1 to n. That's supposed to be an an I. Sorry about that. I'm gonna correct a few things here. That's supposed to be an I. Oops, no, that's not that one. That one was supposed to be an I. And that's it, right? So sorry about that. Let me fix that. So that's an I. That's an I. That's an I, and that's an I. All right. So let's go ahead and apply it. So we have we're gonna plug in here I over n into the function. Well, what is the function equal to? F of x equals x cubed. So you're replacing x with I over n. So that gives us I over n cubed times your delta x, which is 1 over n, the summation from 1 to n as n goes to infinity. And we're going to carry the limit, we're going to carry the notation properly until we apply it. So I cube is I cube, n cube is n cube. Notice that these two are not part of the index I, so we can factor them out. N cube times n is n to the 4. So that gives us 1 over n to the 4 times the summation of I cube. The summation of I cube has a special formula, n squared times n plus 1 squared over 4. You can look that above. And so that whole summation, I'm sorry, let me use a different color. This whole summation is this summation right there, right? From the formulas above. And then we're just going to multiply it by the 1 over n fourth. And our goal now is to simplify this. Now notice that before we can expand this, you can expand this if you want to, but it does make sense for us to simplify them, right? Simplify this whole thing. So the n squared and the n to the 4th will simplify to just be n squared. So now you have 4 times n squared for the denominator, and for the numerator we have n plus 1 squared. Now we're going to expand this, and this will give us n squared plus 2n plus 1 over 4n squared. And then we're going to simplify the terms, right? So it'll be n squared over 4n squared plus 2n over 4n squared plus 1 over 4n squared. Simplify these cancel each other out. This gives us 1 over 4. This cancel partially. That'll be 1 over 2n, and this will give us 1 over 4n squared. So now we can apply the limit. And as the limit, as n goes to infinity, this goes to 0, this goes to 0. So you're left with 1/4 plus 0, which is 1/4. So that gives us the area under the curve. All right. So I hope that you guys find this helpful. There's an example here, practice 6 that I want you guys to try. I gave you guys a hint there. Your hint is how to find your C of I. You guys already know how to find delta x. So delta x is going to be 2 minus 1 over n. So it'll be 1 over n. And so when you guys are finding your C of I, that will be a, which is 1 in this case. Now there's no longer 0, but it's a equals 1. And then plus I times delta x, which is 1 for the a, and 1, and then I times 1 over n, which is I over n. I missed my I here. I'm glad I checked this here. So that's an I, right? I over n. All right. So use this into the equation to simplify it, and try it on your own. And let me know if you have any questions. All right.